edge flex and door closing fatigue failures develop slowly, silently, and almost inevitably in areas subjected to repeated mechanical cycling. Unlike stone chips or impact damage, these failures are not caused by a single event. They result from tens of thousands of low-energy deformation cycles that progressively weaken the coating system at edges, hems, and closure interfaces. Every door opening and closing induces flex. Hinges transfer load into the door skin, inner panels, and folded edges. The outer panel experiences bending, tensile, and compressive strain, especially near edges and along hem flanges. While each individual movement induces only microscopic deformation, the cumulative effect over years places extreme fatigue stress on the coating layers. Edges are particularly vulnerable because film build is inherently lower and stress concentration is higher. Spray patterns deposit less material on sharp radii, and surface tension pulls liquid coatings away from corners during flow and bake. As a result, coatings at edges operate closer to their mechanical limits from day one. When flexing occurs, these thin regions experience higher strain per cycle than flat panels. Microcracking is the earliest manifestation of fatigue failure. At the polymer level, repeated strain causes chain scission and loss of elastic recovery. Initially, cracks are submicron in size and invisible to the naked eye. However, they form interconnected networks that reduce barrier properties, allowing moisture and contaminants to penetrate. Over time, these cracks grow, coalesce, and become visible as edge cracking, crazing, or paint lift. Crosslink density plays a decisive role. Highly cross-linked coatings resist chemical attack and abrasion, but have limited elongation. When subjected to repeated flex, they accumulate fatigue damage rapidly. Lower cross-link density coatings tolerate deformation better, but may suffer from reduced hardness and long-term durability. OEM clearcoat and primer systems are carefully balanced to survive millions of microstrain cycles without catastrophic crack propagation. Primers are critical fatigue buffers. Flexible primers absorb and distribute strain before it reaches the decorative layers. Without sufficient primer compliance, fatigue stress is transferred directly to the base coat and clear coat, accelerating microcrack initiation. This is why edge fatigue failures often appear as clear coat cracking first, followed by adhesion loss and corrosion progression. Residual stress from curing amplifies fatigue damage. As coatings cure and shrink, tensile stress is locked into the film, particularly at edges and fold lines. Each door cycle adds dynamic stress on top of this static preload. Over time, the combined stress exceeds the fatigue endurance limit of the polymer network, even if the coating appeared defect-free at delivery. Additives influence fatigue performance indirectly. Stress relief additives reduce cure shrinkage and lower initial residual stress. Flow and leveling additives help improve edge coverage, reducing extreme thin spots. Flexibilizers increase elongation, but must be used cautiously to avoid compromising mar resistance and gloss retention. No additive can eliminate fatigue failure if geometry and film build are fundamentally unfavorable. Environmental exposure accelerates fatigue degradation. Temperature fluctuations change substrate dimensions, increasing strain amplitude during door movement. Moisture ingress through early microcracks promotes hydrolysis and plasticization, further weakening polymer chains. In cold climates, reduced polymer mobility increases brittleness, making fatigue cracking more severe. Detection of edge fatigue failures requires close inspection and often magnification. Linear cracking parallel to door edges, paint lift at corners, and gloss loss confined to closure perimeters are characteristic signs. Accelerated durability testing combines mechanical cycling, thermal shock, and humidity exposure to reproduce these failures before production release. From a troubleshooting standpoint, fatigue failures are addressed by improving edge film build, optimizing primer flexibility, controlling cure profiles, and minimizing sharp edge geometry. OEM design teams may increase edge radii, modify hem designs, or adjust door reinforcement to reduce flex amplitude. Repainting without addressing cyclic stress sources rarely provides durable improvement. edge flex and door closing fatigue failures demonstrate that coatings are fatigue-limited systems. They must endure millions of deformation cycles while maintaining adhesion, flexibility, and barrier integrity. OEM durability success depends on designing coatings not just for appearance at launch, but for mechanical endurance over the full vehicle life. If you've observed cracking, peeling, or gloss loss concentrated around door edges or closure lines, leave your questions in the comments. In the next episode, we'll continue with multi-material fatigue failures around trims and mirror mounts, where mixed substrates further complicate stress management.